Welcome to lecture series on advanced geotechnical engineering, and we are discussing module 4, shear strength of soils. So in the previous lecture we introduced ourselves to methods for determining shear strength of the soils in the laboratory, and then we said that we have discussed about the direct shear test and what are the the stress states in direct shear test and merits and demerits of the direct shear test. Then we said that the other type of very popular testing, which is triaxial compression test, and which is the physical model test which actually simulates the stress conditions and drainage conditions as in the soil, and it actually has got versatile applications. So in this particular module 4 and lecture 8, we are going to discuss about the different types of triaxial tests and pertinent stress paths. So this is the module 4 in the lecture 8 on the stress strain relationship and the shear strength of soils, and we are as informed we are going to concentrate on the triaxial behavior, particularly with reference to unconsolidated unconsolidated undrained test, unconfined compression test, consolidated undrained and consolidated drained triaxial tests, and the stress paths for the in the triaxial tests. So this, as said, most widely used shear strength test and is suitable for all types of soil, and a cylindrical specimen generally having L by D is equal to 2, because this is required to maintain the principal planes to remain as principal planes during all stages of the triaxial test. Suppose the failure plane passes through the upper and bottom portions, then there can be possibility of the shear stresses generated, and that in such situations those planes cannot be called as the principal planes. So in triaxial test we have this radial plane, which is vertical plane, as well as these horizontal planes. These planes actually remain as principal planes throughout the test, and the typical specimen diameters has been mentioned, 38 mm, 100 mm widely used. Otherwise we also have possibilities of 300 mm diameter, and even the larger sizes triaxial tests are actually becoming in vogue now. So in order to simulate the confining stresses, it is actually done through by filling the chamber with water, and the water is actually pressurized by all round pressure, and which is actually called as the chamber pressure or cell pressure. So this is the typical triaxial cell which is actually shown, and the sample which is having L by D is equal to 2, that is 38 mm diameter or 100 mm diameter and 200 mm height, or 75 mm diameter and 150 mm height is actually placed, and in order to prevent interaction of some sample with the water, there is a membrane which is actually placed, and so that membrane ensures that water tightness, and there are different ports will be there. One port is to the supply water into the soil sample, and one port is to supply to measure the volume changes, and another port is to measure any changes in the pressure within the sample, and the loading is actually applied from the top, that is actually called as deviator load. So when we have the sample which is confined with all round pressures, then the pressures all around for the samples are sigma 3, and then when in order to induce the loading, let us example that we consider an example that we have got a soil strata, and we have got a sample at a certain depth, let us say about 5 meters depth, and above that suppose we are constructing a foundation and the building loading is actually increasing gradually. So that is actually increasing the incremental load is actually applied by this this York and this loading arm, and this loading arm induces that sigma 1. So sigma 1 is equal to sigma 3 plus P by A. So sigma 1 minus sigma 3 is actually called as the deviated load. So in the mechanism basically is that intermediate principal stress sigma 2 must be equal to major sigma 1 or minor sigma 3 stress, so as to facilitate representation of the stress state in 2-dimensional Mohr circle, and a cylindrical specimen is placed inside perspex cell filled with water. So that acrylic cell will be filled with water. The specimen is covered with a latex sheet so as to avoid the direct contact with water, and the specimen is initially loaded by the cell pressure, and then basically during that stage, if the consolidation has to happen, then the consolidation will be allowed, and then thereafter once the consolidation is completed, a deviator stress is then applied gradually on the sample with the help of ram axially. A duct at the bottom of the sample allows the water to pass through the sample, which is further monitored and which actually can have a volume increase, or which can actually measure the volume changes, and the pore water pressure transducer actually measures positive or negative pore water pressures depending upon the stress history of the soil being tested. So fine grained soil can stand the mold without any support, but the coarse grained soil samples have to be kept in some supporting mold until the application of negative pore water pressure to the sample through the drainage duct. So the fine grained soil samples are actually prepared on the without any fine grained soil can actually support, but coarse grained soils or sandy soil samples have to be kept with some suction, and because of that then afterwards the suction is actually released gradually. If the cell pressure is increased to say sigma Cp, then the isotropic pressure is taken entirely by the pore water, and the pore water the pressure increases but no change occurs in the effective stress, because if there is no volume change, then the pore water pressure will no change in the volume, no change in the effective stress. Now we have different drainage conditions, like as has been mentioned, that actually makes the combinations in triaxial test or different types of triaxial test. One is that we have two steps. Step one is that during that consolidation of the sample and then shearing stage. So in this basically there are two stages are there. Stage one where the consolidation can happen, and the stage two is the shearing can happen. Under all round pressures sigma C drainage valve condition will be open if you are allowing consolidation. So the sample the water in the sample drains out. Once the consolidation is actually completed, then it is actually the shear loading. In this also the shear loading actually has got the drainage valve condition can be open and closed. It can be open if you are having a consolidated drained triaxial test, and it can be closed if you are having thinking of consolidated undrained triaxial test, and it can be closed in both consolidation and drainage shearing stages, and that is actually unconsolidated undrained triaxial test. So unconsolidated undrained triaxial test is basically a quick test where the sample is as prepared will be tested without any consolidation by applying three different cell pressures, and if the cell pressure is actually if the sample is actually saturated, and even at different cell pressures the deviatoric load will be same. So with that what will happen is that we get the undrained shear strength of a soil, and the failure plane or the failure envelope will be horizontal. So we have certain practical considerations in which we will be actually doing this consolidated drained and consolidated undrained and unconsolidated undrained triaxial test. For example, for unconsolidated undrained triaxial test, where actually when you are constructing an embankment on the soft soil without any waiting period, that means that you do not allow the consolidation to take place, and you do not allow the even the consolidation during the shear, then a rapid construction on a particular soil deposit on a, let us say, a soft clay deposit actually simulates the unconsolidated undrained condition, or let us say the rapid loading of a founding on a foundation on a unsaturated on a saturated undrained clay is also an indication of the example of unconsolidated undrained test. Or let us assume that a catastrophic failure of in a vertical cut under a saturated soil under undrained condition is also to some extent indicates an example of unconsolidated undrained test. In such situations one need to do the unconsolidated undrained triaxial test, but we have some practical examples in which we can actually say that the different types of tests can be done depending upon the practical situation. The one what we have here is some examples for the CD analysis for clays. This is after Holz and Kovacs 1981, and consider an embankment constructed very slowly, in the sense that embankment constructed in stages, and each stage the consolidation has been allowed, and between each stage there is an adequate waiting period. Then embankment was actually constructed very slowly in stages over a soft clay deposit. So this example, suppose if you are having a situation like embankment construction very slowly in stages over a soft clay deposit, then one has to do the consolidated drained triaxial test, and this also indicates, this is also called the drained parameters, and where the pore water pressure dissipation actually completely occurs. So with that what we call is that these effective shear strength parameters like effective cohesion and effective friction angle can be obtained, and these are actually also indicate for example when we are doing a slope stability analysis, particularly under effective stress conditions, we have to use for the long term stability of a particular slope or embankment, we have to use the we need the effective shear strength parameters like C dash and phi dash. We are actually discussing about the example for some field examples for the where we actually adopt the consolidated drained triaxial test parameters. The other example what we are discussing in this for the CD test, particularly where we can actually get the drained parameters, is the earth dam with steady state seepage conditions, wherein we actually have an earthen embankment or earthen dam constructed with a core and a casing. The casing is actually having material which is medium, the low having low plasticity materials, fine grained soil but with low plasticity materials, and this is the upstream water level, and this is the phreatic surface, and the water flows, and then if through a drain it actually vents out. Now this is the failure surface, typical failure surface. So under steady state CPS conditions, under long term conditions, and then when we wanted to evaluate the stability of an earthen dam subjected to steady state CPS conditions, one need to adopt the effective shear strength parameters, that is C dash and phi dash, especially obtained from by allowing the consolidation, that is the consolidation drainage during the consolidation as well as during shearing stages. So both the stages actually happen very slow. So in a way they give in both the stages what will actually happen is that particularly in the drainage stage, the dissipation of pore water pressure is almost close to zero, because the rise of the pore water pressure will not be there at all, because the drainage is actually happening continuously. The another set of examples, like for example similar situation, we are having an embankment on soft clay, but what we have done is that embankment is constructed after waiting for a period of for consolidation for 1, that is stage 1, and the stage 2 was embankment is raised subsequent to consolidation of a soil under the stage 1 loading of an embankment. So in this case what actually happened is that you actually allowed the consolidation to happen, and during that stage actually drainage is allowed, then volume changes in the soil were actually recorded, but when stage 2 happened and no drainage actually happened, all of a sudden there is a the failure which actually could have arisen. So this actually situation arise, and for this type of situation that we can actually say that consolidated undrained parameters are very useful. And the other example, like the earthen dam example, when you take, we have a core and we have the casing, and this is the water level 1 and water level 2. Assume that the water level 1 to 2 drops suddenly, that is called rapid drawdown case, and in this case rapid drawdown occurs behind an earthen dam and no drainage of the core when it is takes place, that is during steady state seepage conditions the consolidation and all these things has actually happened. The shear tau f is nothing but the shear strength under steady state seepage conditions prior to the drawdown, but what has actually happened is that the drawdown is so sudden, there is no drainage actually during the period of the drawdown. So in such situations the shearing actually happens under undrained conditions. So this is an example for consolidated undrained triaxial test parameters. So here when you have this consolidated undrained case, then in such situations what we can use, that we use these depending upon the typical situations we actually select the type of the test and then we use these parameters for conducting the different special cases of the the triaxial test. So we have in principle consolidated undrained, unconsolidated undrained and consolidated drained triaxial tests, and there is a special case of a triaxial test where unconfined compression test what we call, and which is without any cell pressure, the sample is actually taken to failure. So the specimen is actually taken to failure with no confinement, that is unconfined compressive strength test, and unconsolidated undrained test is actually specimen is taken to failure with no drainage permitted neither in consolidation time nor in shearing stages, and consolidated undrained test actually here the drainage is actually initially open to allow the consolidation to take place and so that the pore water pressure dissipates to 0, and then it is closed so that the failure can actually happen without any drainage. That is the condition where the shearing stage the drainage will be closed. So then third type of test is that the consolidated drained triaxial test. The drainage valve is initially open to allow the pore water pressure to dissipate to the 0. So that is as usual in the previous previous type of test, consolidated and drained test, the sample is allowed to consolidate and the pore water pressure is UI is allowed to dissipate to 0 and is kept open while the specimen is actually taken to the failure at a sufficiently slow rate. So the strain rate at which the samples are actually tested, for example unconfined compression test and unconsolidated drain test, they are actually tested at 1.25 mm per minute, and this is the standard rate, the strain rate at which the sample, this particular 1.25 mm per minute is actually selected. Keep in view that the pore water, no volume changes actually take place and the pore water pressure dissipation also will not actually takes place, particularly in unconfined compressive strength test actually, because it is not actually having exposure, this application of cell pressure, the sample is actually not allowed to undergo the changes due to in the temperatures. So we have in case of consolidated drained and consolidated undrained triaxial test, the strain rates are actually calculated based on the permeability of the soil. Suppose if we are having a marine clay with clay of high compressibility, let us say CH, then in such situations what will happen is that the permeability of the soil is so low, even the test is actually conducted at very slow rate. Suppose if you are having a silty type of soil, the test is actually conducted, the rate, strain rate is selected as the permeability of the silty soil is actually more than clay soil. So the test can be done at a slightly rapid rate compared to the rate at which actually it was done for a clay. So this particular the stresses and strains in a sample in the triaxial compression test, basically it is an axisymmetric condition where sigma 2 dash is equal to sigma 3 dash or sigma 2 is equal to sigma 3 and epsilon 2 is equal to epsilon 3. Epsilon 2 and 3 are nothing but epsilon 2 in the intermediate direction, that is intermediate principal stress direction, and so in case of triaxial test, because of the cylindrical nature of the sample, sigma 2 is equal to sigma 3 and epsilon 2 is equal to epsilon 3. So by using P dash is equal to sigma 1 dash plus 2 sigma 3 dash by 3, so that is nothing but sigma 3 dash, because sigma 1 plus sigma 1 dash plus sigma 2 dash, sigma 2 plus sigma 3. So because sigma 2 is equal to sigma 3, what we have done is that we have written P dash as sigma 1 dash plus 2 sigma 3 dash by 3. In case of total stress, it is P is equal to sigma 1 plus 2 sigma 3 by 3, because P dash is equal to P minus U. Q, that is sigma 1 minus sigma 3, Q dash is equal to Q, because sigma 1 dash minus sigma 3 dash is equal to sigma 1 minus delta U minus of sigma 3 minus delta U. So because of that, sigma 1 minus sigma 3 is equal to Q is equal to Q dash. So thus Q dash is equal to Q, shear is actually unaffected by the pore water pressure. So here when we are actually having a sample which is confined with with the membrane, and then a cell pressure sigma 3, and the axial total stress is sigma 1 is equal to sigma 3 plus P by A. Sigma 3 will be acting in all directions, sigma 3 will be acting in all directions, and sigma 1 is actually applied. So sigma 1 is equal to sigma 3 plus P by A. So the deviator stress is nothing but sigma 1 minus sigma 3 is equal to P by A. That's, so it is also called as sigma 1 minus sigma 3 is equal to sigma D by B by A. And the axial strain in the major principal stress direction, that is epsilon 1 is equal to delta Z by H naught. H naught is the original height of the sample, and delta Z is the vertical compression of the sample, or vertical strain actually experienced by the sample. So epsilon 1 is equal to delta Z by H naught, and radial strain, that is the bulging if it actually happens, for example for a loose sand or for a normally consolidated soil, then there is epsilon r is equal to delta r by r naught. Delta r is the change in the radius of the sample to the original radius of the sample, and the deviated strain is actually given by epsilon d is equal to 2/3 of epsilon 1 minus epsilon 3, and volumetric strain is nothing but epsilon v is equal to epsilon 1 plus 2 epsilon 3. So with P dash is equal to sigma 1 plus 2 sigma 3 dash by 3, and P is equal to sigma 1 plus 2 sigma 3 by 3, and Q dash is equal to sigma 1 minus sigma 3. We will use these deliberations for plotting the stress paths for the different types of triaxial tests. So as we have discussed the the types of triaxial test, and we said that consolidated and drained triaxial test, that is the CD test, which is a very slow test, and if you look into the different stress states in during the sample testing, in the step 1 is that at the end of consolidation, what will happen is that the sample is allowed to consolidate during by allowing the valve to open. So the pore water pressure dissipation will be 0. So then we actually have sigma v dash is equal to sigma v, and sigma dash hc is equal to sigma hc, and during axial stress increase, that with the sigma v and then delta sigma increase, and here as we are not allowing the pore water pressure, the stress state, the shearing is actually done at such a slow rate that the pore water pressure dissipation will be more or less close to 0. In that situation, then we have got sigma v dash is equal to sigma v plus delta sigma is equal to sigma 1 dash. So sigma dash h is equal to sigma dash h is equal to sigma 3 dash. At failure, then these things turn out to be, that is delta sigma turn out to be delta sigma f, then the sigma hc remains constant, and the pore water pressure again still remains constant. At failure, then sigma dash vf is equal to sigma v plus delta sigma f is equal to sigma dash 1 sigma 1 f, that is the failure, and sigma dash h f is equal to sigma dash h is equal to sigma dash 3 f. So this is the principal stress in the radial direction at failure, and sigma 1 dash f is the principal stress in the direction, the major principal stress direction. So sigma 1 is equal to sigma vc plus delta sigma, and sigma 3 is equal to sigma hc. The deviator stress or deviator is given by q, or delta sigma d is equal to sigma 1 minus sigma 3. So during the consolidation, consolidated drained triaxial test, or if we are having a CU test, the volume change actually takes place. So this particular volume change of the sample during the consolidation, so till the consolidation is completed, the sample is actually allowed to consolidate, and thereafter once this consolidation is completed, once the consolidation stage is completed, Typically for a clay, it may last for about more than 4 to 5 days or sometimes about a week for completion of consolidation. And in this particular slide, the stress strain relationship during shearing is actually given, and this is for a case of for the case of consolidated undrained triaxial test, wherein here what we have done is that we actually have not allowed the drainage to take place during the shear, and then what you can actually happen is that we have a situation that here the deviator stress actually variation is like this, and then there is a decrease, and decrease actually takes place. So this is for valid for dense sand and OC clay, and this is for the loose sand or normally consolidated clay. You can see that dense sand and OC clay, there is a hardening takes place, and after attaining a peak, a distinct peak is actually after exhibiting the distinct peak, there is a a softening actually takes place. So here in this case what will actually happen is that here this is actually for CD test, that is for consolidated drain test, and wherein actually here the sample, if you can see that loose sand or normally consolidated clay, there is a compression actually takes place, but in case of dense sand and over consolidated clay, initially there will be some compression, thereafter there is an increase in volume, that is volume actually increases. So this is actually because we have discussed earlier the dilutancy behavior of the soil. So in case of triaxial test also, particularly when you are actually allowing the sample volume to change during the shearing by allowing the drainage to happen, that is in the case of consolidated drain test. So what will happen is that you actually have got the volume changes actually takes place in the way which is actually shown, but during all stages the pore water pressure remains to be same, the pore water pressure remains to be same. And the CD test, when you actually have done say if you wanted to see how actually we can determine a different the parameters, the shear strength parameters. So what one need to do is that we have to do let us say minimum 3 samples or 4 samples, and each sample is actually tested for different cell pressures or different confining stresses. So confining stress 1, that is sigma 3a, and confining stress B is say sigma 3b, and confining stress C is sigma 3c. Then we actually have got different types of the stress deviator stress versus axial strain curves. So once you know the maximum or peak values, and for those peak values that is, this is nothing but the delta sigma d. So we can actually with that as this as diameter, one if you draw the Mohr circle, you actually can draw different Mohr circles, and depending upon let us say that if it is normally consolidated soil and which are loose sand, then actually we have a situation like C dash is equal to 0, it passes through the horizon, and tau sigma envelope will be like this, with where pi is equal to pi dash here, which is the angle of inclination of the Mohr Coulomb failure envelope. See when this actually interacts with this thing. So this is the failure plane, which is nothing but 45 plus 5 by 2 inclination which actually happens, and this is the angle of inclination of the failure. So this is the typical, so you need to have these the parameters basically to determine different types of sets of Mohr circles can be drawn with the different cell pressures and different deviated loads, and so in case of when you consolidated drain test, as the cell pressure is increased, the Mohr circle diameter keeps on increasing, a deviator load keeps on increasing. So the strength parameters C and phi obtained from CD test, since U is equal to 0 in consolidated drain triaxial test, sigma is equal to sigma dash, and therefore the C is equal to C dash and phi is equal to phi dash, and what we call these are CD and pi d, there is nothing but drained cohesion and drained angle of internal friction which is called, and these parameters basically represent the long term conditions in a soil where consolidation is actually allowed and then drainage actually taking place during the application of the loading period. So in such situations the consolidated drain test, the parameters are actually are vital. For strictly speaking, for example, if you are having a normally consolidated clay, if that is actually identified as normally consolidated clay, and as CD is equal to 0 and more circle is actually passing through the horizon, the failure envelope actually passing through the horizon. Therefore, one CD test would be sufficient to determine the pi d of the sand or loose sand or normally consolidated clay. So one CD test would be sufficient to determine the pi d, the drain friction angle of a loose sand or normally consolidated clay. For over consolidated clays, for the soils which are actually have been subjected to certain pre-consolidation pressure, the CD of a over consolidated soil is not equal to 0, or when you are actually having a very dense sand or dense sand deposits, and where in that case also the CD not equal to 0. So over consolidated clay and normally consolidated clay, when we look into this here, initially up to pre-consolidation pressure, the envelope actually, the more Coulomb failure envelope runs like this, that beyond that it actually changes into the normally consolidated this is valid, like it joins with the normally consolidated failure envelope. So the point of transition where it actually changes again, the behavior is actually like the pre-consolidation pressure, that is sigma c, and wherein up to that pre-consolidation pressure stage, the sample actually exhibits a drained cohesion, and then thereafter once it crosses sigma c, and there is a possibility that it actually merges with the normally consolidated more Coulomb failure envelope. Now let us discuss about the stress paths during the CD test. So what we have drawn is that we said that there are two stages. So we have actually represented here Q sigma 1 minus sigma 3 and P is equal to sigma 1 plus 2 sigma 3 by 3, or P is equal to sigma 1, P dash is equal to sigma 1 dash plus 2 sigma 3 dash by 3, because P and P dash are indicated here. So during the initial stage, that is consolidation phase, what it has been indicated that the stress path actually follows from here to here, and thereafter it is subjected to shear. So this is during the shearing stage. So the shearing stage actually starts from here, and this inclination of this is actually indicated as 3 to 1, 3 vertical 1 horizontal. So if you look into this here, this delta sigma 1 is equal to delta sigma 1 dash, because no load is actually applied, and delta sigma 3 is equal to delta sigma 3 dash. So delta sigma 3 is equal to delta sigma 1 dash and delta u is equal to 0. So the consolidation phase actually is indicated here. So delta sigma 1 is equal to delta sigma 1 dash is equal to delta sigma 3 is equal to delta sigma 3 dash, and delta sigma 1 greater than 0, delta u is 0 at the end of consolidation. So during the consolidation, once it is self pressure is applied, the pore water pressure increases to the excess pore water pressure, and then it dissipates. So that is at the end of the consolidation, the delta u is equal to 0. With that, what will actually happen is that delta p dash is equal to delta p is equal to delta sigma 1 plus 2 delta sigma 1 by 3. So if that it gets simplified to delta p is equal to delta sigma 1, and delta q is equal to delta sigma 1 minus delta sigma 3, as delta sigma 1 is equal to delta sigma 3, delta q is equal to 0. So delta q by delta p dash is equal to delta q by delta p is equal to 0. So because the slope of this is actually 0, it actually passes along the p dash line, that is q is equal to 0 line, it actually passes, and subsequently what actually happens is that the sample is actually subjected to subjected to shearing. So here during the shearing phase, sigma 3 is equal to sigma 3 dash, delta sigma 3 is equal to 0 and delta u is equal to 0, because no pore water pressure changes are actually allowed, because the sample is not subjected to very slow shearing rate, and sigma 1 dash is equal to sigma 3 dash plus p by a. So with this this also indicated as the effective shear stress path and the total stress path, both are actually identical in this case. So for For the case here stage 2, delta sigma 1 is equal to delta sigma 1 dash greater than 0 and delta sigma 3 is equal to delta, so we are not actually changing the cell pressure, so delta sigma 3 dash is equal to 0 and delta u is equal to 0 during the shear stage, so delta p dash is equal to delta p with delta sigma 1 and remaining other things are 0, delta sigma 2 and delta sigma 3 is 0. So with that what will actually happen is that delta sigma 1 by 3 is the what we get. So this is actually delta sigma 1 by 3 and delta q is equal to delta sigma 1 minus delta sigma 3. So this is equal to delta sigma 3 is equal to 0, what you have is that we have only delta sigma 1. So delta q by delta p dash is equal to delta q by delta p is equal to because of delta q is equal to delta sigma 1 and delta p dash is equal to delta sigma 1 by 3 which is nothing but delta q by delta p is equal to 3. So because of this reason what you can see is that delta p is equal to delta sigma 1 by 3 or delta q is equal to delta sigma 1. So delta q by delta p is equal to is given as 3 here, that is the 3 vertical 1 horizontal. So next we introduce ourselves to the consolidated undrained triaxial test, and wherein we said that during consolidation the drainage is actually allowed, but during the shearing the drainage valve is actually closed. So shearing is done to represent a particular case where the practical cases or examples have been discussed earlier. So this is for total and neutral and effective stress. So here as we are actually not allowing the drainage in the shearing stage, so depending upon the stress history of the soil the pore water pressure changes occur accordingly. Suppose if you are having a normally consolidated or a loose sand sample, their pore water pressure will be positive, and in case we are having a war consolidated soil or a very dense sand sample or dense or very dense sand sample, the pore water pressure is actually negative after initially positive and then subsequently changes to negative. So at the end of the consolidation the pore water pressure is actually 0. So then the effective stress is sigma dash Vc is equal to sigma Vc, sigma dash Hc is equal to sigma Hc. Then during the axial stress increase the pore water pressure is can be plus or minus delta u, it can be positive or it can be negative. Depending upon that the changes sigma dash V is equal to sigma Vc plus delta sigma plus or minus delta u is equal to sigma 1 dash, and sigma dash H is equal to sigma Hc plus or minus delta u is equal to sigma 3 dash. So at failure, so you can see that during the stress increase the drainage is actually closed here. So because of that the sample is not allowed to drain, then because of that there is a changes in the pore water pressure, and at failure again no drainage. So with that again the failure shear stresses are the pore water pressure changes are plus or minus delta uf. So sigma dash f is equal to sigma Vc plus delta sigma f plus or minus delta uf is equal to sigma dash 1f, and similarly in the horizontal direction sigma dash hf is equal to sigma hc plus or minus delta uf is equal to sigma dash 3f. So the volume changes in the sample, which is actually same as the consolidated undrained triaxial test, which is similar, and in this case CU test the stress strain relationship during shear, which is again very similar to that, but only thing is that here the pore water pressure variation which actually takes place like this is positive and the pore water pressure is negative if you are having a dense sand and war consolidated clay. So in this case when you have CU test basically to determine the shear strength parameters, here we can actually get total strength parameters as well as effective strength parameters, and for example for the first case which is actually shown here, the total strength parameters how to obtain actually shown here, and we are having a case where two confining pressures which are actually shown, sigma 3a and sigma 3b, and two more circles are shown, and when the envelope is actually drawn, this is the Mohr column envelope for the total stresses and this is the Mohr circle, but depending upon the pore water pressure depending upon the variation of the pore water pressure, we can actually get the Mohr circles accordingly, positive or negative. So with that what will happen is that we will get the effective strength parameters, that is the Mohr Coulomb failure envelope shifts accordingly. And so this is for the strength parameters for C and phi in case of so with the consolidated undrained triaxial test we get both drained parameters as well as undrained parameters. So the shear strength parameters in terms of total stresses are actually called as C consolidated undrained and phi Cu. In case of shear strength parameters in terms of effective stresses are called as C dash and phi dash. So C dash is equal to CD and phi dash is equal to phi D. They are called the drained friction angle and drained cohesion. So the stress paths for the consolidated drained triaxial test. So we have seen consolidated drained triaxial test, and in the case of consolidated drained triaxial test we notice that the stress paths for the effective stress path and total stress paths they both look alike, but in case of the consolidated undrained test where the shearing changes actually happens. So because of that during the shearing the pore water pressure changes actually happens. So the effective stress path actually runs like this schematically, which is shown here. So we have isotropic consolidation phase, delta U is equal to 0 and delta P dash is equal to delta P is equal to delta sigma 1 plus 2 delta sigma 1 by 3, which is nothing but delta sigma 1. So delta Q is equal to delta sigma 1 and delta sigma 3, with delta sigma 3 is equal to 0 and delta sigma 1 is equal to 0 here, delta Q by delta P dash is equal to 0. So with that what will actually happen is that delta Q is equal to delta sigma 1, and so with this actually what will happen with the delta Q is equal to 0 and delta P is equal to delta sigma 1, delta Q by delta P dash is equal to delta Q by delta P is equal to 0. So the in this case also during the consolidation phase the stress path actually runs like this. Then depending upon effective stress path means it runs like this, total stress path means it runs like this. So here in this case again delta P is equal to delta sigma 1 by 3 and delta Q is equal to delta sigma 1. So delta Q by delta P is equal to 3. So this actually runs like this. So this is for the shearing stages which are shown, and this is for the initial consolidation phase which are actually shown. So for effective stress parameters and for effective stress paths and total stress path, the shearing phases is actually indicated here. Delta sigma 1 greater than 0, wherein delta sigma 3 is equal to 0. So delta sigma 1 dash is equal to delta sigma 1 minus delta U, which is equal to 0, and delta sigma 3 dash is equal to minus delta U, and delta P is equal to delta sigma 1 by 3 is equal to delta sigma 1. So delta P is equal to delta sigma 1 by 3 and delta Q is equal to delta sigma 1. So delta Q by delta P is equal to, which is nothing but delta sigma 1 by 3 the delta sigma 1 by delta sigma 1 by 3 becomes 3, that is for total stress path. But in this case delta P dash is equal to delta P minus delta U, which is nothing but delta sigma 1 by 3 minus U, that is what we have done is that delta U, the pore water pressure change actually has been subtracted, and delta Q is equal to delta sigma 1 where delta Q by delta P dash is equal to delta sigma 1 divided by delta sigma 1 by 3 minus delta U. So that is when you simplify that one, because this is different. So we have 3 divided by 1 minus 3 to the ratio of delta U by delta sigma 1. So because of this particular variation, the effective stress path actually runs like this. Now as we said that we have another class of the triaxial test, which is a quick test, which is actually called unconsolidated undrained triaxial test. The purpose of the unconsolidated undrained triaxial test is to determine the undrained shear strength of a soil, of a saturated soil. Predominantly if it is saturated, then we actually have the undrained cohesion of a or undrained shear strength of a soil. So this is a quick test, so neither during consolidation nor shearing stage excess pore water pressure is allowed to drain, but there is a possibility that the pore water pressure develops but is not allowed to drain. So this indicates these are sometimes you actually get for catastrophic loading or sudden loading, the shear strength parameters, these parameters which are actually obtained from this can be used for the design. So this is basically for short term considerations, this can be applied. So different stress states or conditions are actually shown here. So this is actually the sample as prepared, the 0, the effective total stresses on the sample on outside 0, the pore water pressure inside the sample is actually negative, and then because of that sigma dash V is equal to positive UF will be there. So because of that negative pore water pressure, the sample actually stands vertical. So the effective stress here is that sigma dash V0 is equal to UF, sigma dash H0 is equal to UF. So all round actually it maintains an effective stress of equivalent to the negative pore water pressure which is actually there in the soil. And after application of the hydrostatic cell pressure, then what we have done is that we applied sigma C. The total stresses on the sample changes to sigma C and sigma C here. Now the pore water pressure here is nothing but minus UF, that is negative, plus delta UC, because we applied sigma C, because of that there is an increase in soil sample pressure, and 100% saturation means the water actually attracts the load, and then sigma dash V C is equal to sigma C plus UF minus UC. So this is another set of this thing will come, and the sigma dash HC is equal to UF will be there. During the application of the axial load, these are the stress states, which is nothing but because of the shear there is an increase in the pore water pressure that gets added here. So the stress states actually different stages, actually the stages are given. One is just application of the just placement of the sample before application of cell pressure, then other one is actually after the application of cell pressure, and then during the application of the shear load, and then at failure. So the more circles are for the 100% saturated clay are indicated like this. So you can see that this is independent of the whatever the cell pressure we apply. For example, this is a case where 0 cell pressure, but when you actually have a cell pressure of say 50 kilopascals, 100 kilopascals and 200 kilopascals, and if the soil is completely saturated and unconsolidated undrained test is performed, then you actually have a case where you get the horizontal failure envelope, that is Mohr Coulomb failure envelope, the pi t is equal to 0 or pi u is equal to 0, and so the tau f is equal to shear strength is equal to Cu, and that is the Mohr Coulomb failure envelope will be horizontal only. So this indicates that the stress is actually independent of that stress. So whatever may be the confining pressure you apply, that much deviator load is generated such a way the diameter of the Mohr circle remains constant. Say for example, when you are having a partially saturated clay, and initially when you do unconsolidated undrained test using with partially saturated samples, then actually you got when degree of saturation is less than 100%. So with the high high cell pressures, when you have high confining pressures, and because of the cavitation, actually what happens is that the water is actually the air which is within the sample is shunted out with water. So what will happen is that the 100% saturation is actually ensured. So and at very high confining pressures, the Mohr Coulomb failure envelope tend to become horizontal. So then the sample actually becomes 100% saturated. So in that case again it maintains the horizontal plateau for the Mohr Coulomb failure envelope. Otherwise initially for partially saturated samples, actually you have got curvilinear Mohr Coulomb failure envelopes can actually happen, and sometimes people mislead by using these values for Cu and phi u as strength parameters under undrained conditions. So the total stress paths during unconsolidated undrained triaxial tests are actually given here. So in this case, because neither consolidation nor shearing stage there is a drainage. So what is actually happening is that the stress path actually starts directly here. This is a total stress path only, and where you have sigma 1, this is the sigma 1 is equal to sigma 3 plus p by a, and sigma 3 and delta u is not equal to 0. So initial stage is that delta sigma 1 is equal to delta sigma 3 and delta u is not equal to 0. So delta p is equal to delta sigma 1, delta q is equal to 0. So delta q by delta p is equal to 0, that is at this point. At the shearing phase, delta sigma 1 is greater than 0 and delta sigma 3 is equal to 0. So delta P is equal to delta sigma 1 by 3, delta Q is equal to delta sigma 1. So with this again, the inclination of this is delta sigma 1 by is again 3. So delta P is equal to delta sigma 1 by 3, delta Q by delta P is equal to 3. So as we have been discussing that there is also unconfined compressive strength test. This is one thing basically to determine the undrained shear strength of a saturated clay very quickly, and in this case is a special case of triaxial test which is called with sigma 3 is equal to 0, the cell pressure is actually 0. So in this particular slide where a sample actually loaded which is actually shown with sigma 1, that is the deviated load, because sigma 3 is equal to 0, and the sample is actually not confined with the chamber pressure. So in this case basically this is a quick test where it can actually give undrained shear strength of a saturated sample. Sometimes this is also used for partially saturated soils basically to get the unconfined compressive strength of a sample, and then there afterwards you can actually get the undrained cohesion. The sample need not be completely saturated, but truly speaking it should be to determine the undrained shear strength of a saturated clay quickly. And the deviated load is actually increased rapidly until the soil sample fails. Pore water cannot drain from the soil, so the sample is sheared off at the constant volume. The sample is actually sheared at constant volume without any changes in the volumes and without changes in the pore water pressure. So these test states are actually given here as the sample is prepared. This is same as unconsolidated undrained triaxial compression test, and this is neutral stress or pore water pressure is minus UF. So initial effective stress is that sigma dash V naught is equal to UF. Similarly, during the application of load you can see that there is a pore water pressure change occurs, but not allowed to drain. So the test is actually done such a way that no dissipation of pore water pressure takes place, no volume under no volume change conditions. So sigma dash F is equal, sigma dash V is equal to the delta U plus UF, that is the UC, that is during the initial conditions. So this is at failure conditions. So the total stress path during unconfined compression test, again it actually resembles to this. It actually passes through the origin, and if delta U is measured, it would have been negative, since it would be negative since sigma 3 is equal to 0. Delta sigma dash 3 is equal to sigma 3 minus delta U is equal to minus delta U. So delta U must be negative because as sigma dash 3 cannot be negative, so soils cannot actually sustain tension, so sigma 3 must be positive. So the effective stress path is unknown in case of unconfined compressive strength test, because the pore water pressures or changes are not normally measured. They are not measured normally. If delta U is measured, it would be negative since sigma 3 is equal to 0, and this delta U must be negative because as sigma dash 3 cannot be negative, the soils cannot sustain the tension. So the sigma dash 3 must be actually positive. So here the delta U, if at all you measure during unconfined compressive strength test, the pore water pressure will be negative. And the resultant Mohr circles for the unconfined compressive test are actually gone here. So this is the total stress circles, because this starts from origin because sigma 3 is equal to 0, and this is the Mohr Coulomb failure envelope, and this is the total stress Mohr circle, and if at all means the effective stress will be like this, the effective stress Mohr circle towards the right side because delta U is negative, and if it is positive it comes this side. So the effective stress circle cannot be determined in the UC test, this is only just indicated here, and this is as the phi U is equal to 0, the failure plane is actually only 45 plus phi by 2, it is only 45 degrees. So the failure plane is actually indicated here, and this point where it actually intersects, that is actually the horizontal envelope of a Mohr Coulomb failure envelope. So the Cu is actually shown here. So basically the results from the UC test are actually can lead to the usage of the estimate of the short term bearing capacity of a fine grained soils for foundations, and basically for unconsolidated and drain test also we can use this logic, and estimate the short term stability of the slopes or earthen dams, and determine the stress strain characteristics under fast undrained loading conditions. So if you wanted to see the stress strain characteristics of a material under fast loading conditions, and this actually particular test is actually used. So this is a typical variation of sigma 1 with UC1. So you can see that the sample where the failure surface is actually is about is inclined like this, and so you can see that this is sigma 1 and this is epsilon 1, and so the average of these two values, which actually gives, this is the deviated load, sigma 1 by 2 gives the 136 by 2, which actually gives the undrained cohesion of a soil sample. So in this case this is a partially saturated soil, which is actually having you can say silty clay type of sample, where you can say that the undrained cohesion is about 65 kilopascals. So we also have some results which are actually typical results of consolidated undrained triaxial tests on silty sand samples are actually shown here. So you can see that the sample is actually tested with 3 different cell pressures, 50 kilopascals and 100 kilopascals and 150 kilopascals. So this is actually 50 kilopascals cell pressure with it tested at sigma 1 minus sigma 3, and this is at 50 kilopascals, 100 kilopascals and 150 kilopascals, and this is the excess pore water pressure measured, because this is mostly you can actually see that the pore water pressure is positive, because this is a close to normally consolidated sample state. So the sample at the end of the shear, you can see that the sample actually has undergone major portion of bulging, and then the subsequent shear failure actually happened. This is actually within the membrane, and once the membrane is actually taken out, this is the case. And then the stress paths actually are drawn here with the P is equal to sigma 1 plus 2 sigma 3 by 3 from the test data which is actually obtained. So these are the total stress paths, that is for 50 kilopascal cell pressure, 100 kilopascals and 150 kilopascals, and then these are the stress paths for the effective stress for 50, 100 and 150, and these are the Mohr circles for the silty sand sample which is actually tested. So the sample found to have the undrained parameters of the undrained parameters are C 7 kilopascals and 532 degrees, and the drained parameters which is 2 kilopascals and 35 degrees. So this is the drained parameters, and this is for example of a consolidated undrained triaxial test on a fine sand having a maximum void ratio 0.778 and 0.54 to minimum void ratio, and the void ratio after the consolidation stage is very dense nature, and deviated stress versus axial strain is shown for 2 different cell pressures 50 and 100 kilopascals, and this is the pore water pressure. Here you can see that because of the dense sand, the pore water pressure variation is actually negative. Then these are the typical stress paths. In this particular slide, we are seeing a status of sample, particularly very dense sand sample after termination of consolidated undrained triaxial test. So you can see that the sample bulging as well as the shearing actually which has taken place with pi by 4 plus 36 by 2, 45 plus 45 plus 36 by 2, that is the angle of inclination of the failure plane, about 63 degrees is the failure plane, and wherein you can see that the dense sand sample actually exhibits the failure plane which is distinct failure plane, and when you actually have loose sand and normally consolidated soils, we have predominantly bulging actually takes place. So in this particular lecture, what we have done is that we try to understand about the different types of triaxial tests, particularly unconsolidated and drained triaxial test, and consolidated and drained and consolidated drained triaxial test, and unconfined compression test is special case of so all these tests which actually we have done for for a compression case, and we know that by maintaining different combinations of cell pressure and axial pressures, we can also do extension test by using the triaxial compression test. But in this particular case, mostly we have covered about the unconfined compression test or UU and CU and CD triaxial compression test pertinent details, and then we also discussed about the the stress paths pertinent to that with the Q and P and P dash, and then we also have discussed about how we can actually determine the drain parameters and undrained parameters depending upon the situation, like for example undrained bearing capacity, or when you actually have short term stability of a slope, then we can actually think of using undrained parameters, undrained strength parameters. When you wanted to have a long term stability of a slope or long term stability of an embankment, then long term bearing capacity, then we actually have to use and the effective strength parameters like drain parameters C dash and phi dash.